Part 4. You will hear a lecture about advances in desalination technology. First, you have some time to look at questions 31 to 40. Now, listen carefully and answer question 31 to 40.
Good morning, delegates. My presentation today addresses critical developments in desalination, converting seawater into freshwater. With global water scarcity affecting 2 billion people, this technology offers vital solutions for coastal regions worldwide. Traditional desalination began in ancient Greece, where sailors boiled seawater using bronze cauldrons. Modern industrial processes emerged during the mid-20th century. The multi-stage flash process dominated early facilities, requiring temperatures of 100 degrees Celsius. These plants consumed enormous energy, approximately 15 kilowatt-hours per cubic meter of water produced. Today, reverse osmosis leads the industry. This method forces seawater through semi-permeable membranes using high pressure. Modern plants operate at 70 bars pressure, achieving 45% recovery rates. Energy consumption dropped to 3.5 kilowatt-hours per cubic meter, a 75% reduction since 1980. However, significant challenges persist. Membrane fouling occurs when biological material clogs filters, reducing efficiency. Chemical cleaning requires monthly shutdowns, costing facilities approximately $200,000 annually. Brine disposal presents environmental concerns. Concentrated salt discharge damages marine ecosystems, killing seagrass beds and affecting fish populations. Recent breakthroughs address these limitations. Researchers at MIT developed graphene membranes in 2012. These single-atom thick filters allow water molecules through while blocking salt ions. Laboratory tests demonstrate 50% faster flow rates than conventional polymers. Commercial availability is expected by 2028. Solar desalination represents another promising avenue. The Sundrop Farms facility in South Australia operates entirely on concentrated solar power. Using 23,000 mirrors, the plant generates 39 megawatts daily while producing 1 million litre of freshwater. This carbon-neutral approach eliminates grid dependency entirely. Biomimetic designs copy natural processes. The Namibian beetle collects morning fog using hydrophilic bumps on its shell. Engineers at NBD Nano replicated this surface pattern, creating materials that harvest 2.5 liters daily from air humidity. Similarly, mangrove roots inspire filtration systems removing 99% of contaminants without membranes. Forward osmosis offers lower energy alternatives. This process uses concentrated solutions, typically ammonium salts, to draw water naturally through membranes. The Oasis Water Company implemented this at PetroChina facilities, reducing energy costs by 90%. However, draw solution recovery requires additional thermal steps. The Megaton Water System project in Japan targets agricultural applications. Conventional desalination produces water too mineral deficient for crop irrigation. This system adds precise nutrient concentrations, creating hydroponic solutions. Trials with tomato cultivation showed 30% yield increases compared to groundwater usage. Economic analysis reveals shifting cost structures. Traditional plants required 1.50 * per cubic meter. Modern facilities achieve * 0.50 through renewable energy integration. The Sorek plant in Israel, world's largest, produces 624 million liters daily at 40 cents per cubic meter. Desalination now undercuts water imports in Caribbean nations and Pacific islands. Future directions include capacitive deionization. This electrical technique removes salt using charged electrodes rather than membranes. Lawrence Livermore laboratory prototypes show 80% energy reduction for brackish water treatment. Scaling to seawater salinity remains challenging. Atmospheric water generators bypass oceans entirely. These devices condense water vapor from air using Peltier coolers. Zero-mass water installations in Arizona produce 5 liters daily per panel. While currently expensive at $2,000 per unit, costs should drop with manufacturing scale. Policy implications are substantial. Saudi Arabia currently meets 70% of domestic needs through desalination. The NEOM project plans 100% renewable-powered facilities by 2030. California recently approved 17 new plants despite environmental opposition. To conclude, desalination technology advances rapidly towards sustainability and affordability. Integration with renewable energy, biomimetic engineering, and circular economies promises water security for future generations. Thank you.
This is the end of the test. You now have half a minute to check your answers.